So this is our Aster-Study module. We have already created the mesh in the last tutorial. So now we will set up the Code-aster-Study, and for that first we will read the mesh. What we had done was in the current case we had added a stage, and in this stage now I have this mesh, model definition, material, etc. Okay, so first we need to read the mesh. So read a mesh. It is asking me the mesh file location. As I told you already, in this, wherever this red star is there, it means it is a mandatory argument. It must be available. So for mesh file location, I can open the mesh file, which is mesh 1. So let us open it, and this mesh has come. Its format is made, so I am clicking it. Then the remaining things are not much necessary now, so we say to OK, and it has given me the necessary command here, liagimayaz, that means read the mesh in format made from the file logical number, logical unit 20. Okay, this is the unit number usually used for reading the mesh file. Then what I need to do is, since I am going to apply some pressure load on this surface, therefore in Code-aster what we need to do, whenever there is a plane or any surface, the direction of the surface is given by the normal to the surface, the vector that is normal to the surface. And the Code-aster requires that whenever we want to apply some load on some surface, its normal must be outward. Okay, the orientation of the surface must be in such a way that its normal must point towards outward, not inward. Okay, so while meshing it, the direction of the surface may be towards inside also. Okay, it is basically obtained by cross product of these two vectors. Say this surface will be obtained by the cross product of these two vectors. Okay, now depending on the node numbering, these two vectors may be either this direction and the other may be in this direction. So as per the right hand rule, the outward normal may not be outside, the normal may not be outward. So what we need to do, we need to modify the surface where I want the load to be applied in such a way that its normal is outward. So for that purpose, what I need to do, I need to modify my mesh, and this is the command, modify the mesh. If you hover it, you can see here, you can read here in the pop-up menu that modify a mesh, modimayaz or modimayaz. So I select this. Now it says me that which mesh I should use. I should use the same mesh, and therefore I have to use reuse the object. So it is already ticked. That means the same mesh will be modified. Then I need to use, in this case, since this is a 3D mesh, therefore I say ori pu 3D. Ori means orient, pu means it's the French word, some word for the skin. Okay, I do not know the full word, but pu means skin here. So orient the skin in 3D and for that I have to give the group of skin or group of face. So I will edit. So it is asking me group of element, and this is must be given because the red star is there. So I click yes, then I click top, and the top this thing is selected by yellow. Now if I select this, click this, then it will show the faces orientation vector, and you can see that all these vectors are now outward. If I sufficiently enlarge it, you can see that they are outward now. Okay, so that's how we can orient the vectors. Then I say OK, and one more OK, one more OK. So the mesh has been modified. Until the full command is correct, this will become red, and once it is ready, and you will get warning also if you want to save without giving all the arguments. Okay, so this is the command file. In the command file this thing will be written. Modi mail is the mail is that same mesh, and OUP3D, it is the group of mail means mesh or element here, so group of element is top. Now next job our is to define the model. Define the model means, you see the mesh is, we have generated the mesh, but the mesh is not yet the part of my FEM model which I am going to solve, and therefore what I need to do, I need to assign this mesh to my model that I want to analyze. Therefore I must go to this model definition, then I will call it assign finite element. Okay, assign finite element. If it is not much visible, you can go there, model definition, assign finite element. Now in the assign finite element, what it asks that in this small box it is saying at least one. That means I need to say which group of element will be added to the model and what type of modeling will be done. Okay, so for that it asks me at least one factor of this, at least one argument of this, which is the finite element assignment. Okay, and which is the mesh. This is also a mandatory element, but it is already selected, but this layer mail is selected. I should use the Modi mail is here. Okay, this mesh I should select, and here I will use finite element to be assigned. I have to add one item, edit. So it is asking me where exactly one, everywhere or some group of element, and I am going to assign 3D element for everywhere. So I'll select everywhere here. Everywhere is yes, and which phenomenon I want to use, mechanical analysis. You know that Code-aster solves mechanical, thermal and acoustic. So you have all these three here, acoustic, mechanic and thermic, and we are doing mechanical analysis, so I am selecting mechanic. And then it is asking me which type of model I want. Say whether this is a shell element, whether this is a 3D element, whether it is a beam element, something like that. So in the modelization, I need to add out of all these types of modelization, various types of models. There may be all these types of models in mechanical. And out of that, 3D I will select. Then I will say OK. Then again OK. So now it is the command file is saying that affe model, that means assign model, effect modelization, that means assign model. And what is the modelization type? It is 3D. What is the phenomenon you are analyzing? It is mechanical phenomenon. Tout equal to oui means, tout means all, and oui means yes in French. So everywhere it is yes. And from which mesh you should read the elements? From whatever is the mesh. This is my mesh. Okay, the name here is mesh, and same mesh I am giving to the model. And this concept has created a model now. Okay, next I need to go for material definition. I must define some material. Okay, that means the constitutive material. I must specify which constitutive law it should follow. We will use simple linear and elastic analysis so that it can be completed quickly. So then we go for defining a material, define material. Okay, or here you can go commands, material, assign a material, define a material, and there are many other options for that. So define a material I will select. Now there are all these various types of materials available for mechanical analysis. Okay, huge number of materials, as I told you, and in every material, every type, there are some subtypes. Okay, so I will use linear isotropic elastic material. Now I will edit, and it is asking me Young's modulus and the Poisson's ratio. Now you remember that we used the mesh in millimeter units, so I will give my Young's modulus in Newton per millimeter square, or MPa unit. And if I use still, you know that modulus of elasticity, Young's modulus of still is 2.1 10 to the power 5 MPa, or Newton per millimeter square. So that is what I will give, 2.1 E05. And the Poisson's ratio I can give 0.3. And if I want to analyze for self weight also, I can give density here. And if I want to do study for thermal behavior, then I can give thermal expansion coefficient also. But right now these are not necessary, so I am not selecting them. And then I am saying the material name, you can say it is still. I can name it, then I say OK. Okay, so the material has been defined. Now I need to assign this material to this model. So for that I will use affe material. So material, assign a material, assign a material, and this name is filled material. Okay, steel was the actual material we have defined, but in the model which material is being used is called filled material. Okay, or any other name you can give. So it needs at least one of this mesh or model. I can give both of them. This mesh is modi mail I should use, and model is affe modeli. It automatically selected, and then I should assign the material. This is another mandatory argument because there is red star, so I must add one item here. So where I should give, the whole box is made up of steel, so everywhere is yes. And which material? The material is steel, that is already defined. If you have many materials, then you will get all of them in this drop down menu. Okay, so I have selected steel for everywhere, and I have saved. that I have assigned the material. The command is affe material. Material is still, tout is we, that means everywhere the still is there for this mesh and for this model. Okay. Then what I need to do is, this is called functions and lists. This is for loading step, and in this linear elastic analysis we do not need any kind of loading step. The whole load will be given in single step, so I don't need to use this item. Then comes BC and load, binary condition and load. And here again everything is not visible here. In Linux everything is readable. I'll go to this thing and BC and load. So it says assign mechanical load. Remember in Code-aster, boundary condition is also taken as a mechanical load, because those boundary conditions you will according to that you will modify the matrix, stiffness matrix, as well as the load vector, if you remember correctly, okay, or deformation vector. So you have already done those things in while you studied FEM in 5203. So let us assign the mechanical load. This is load. I can specify both boundary condition and the pressure load in the same load statement, or I can use two separate statements. So it is better to apply two separate statements for readability or understandability. So I will say it is BC, boundary condition, and the boundary condition for this, these are the things: enforce DOF, enforce some degree of freedom. Okay, so I will select this and I must specify, so I need something more. So one item I am editing. Okay, now it is asking me which group of element or node you want to apply that degree, that enforced degree of freedom. And here it is saying liaison encastre, that means it is fixed. And I want my bottom face to be fixed because this is my loading face. So I will say group of node. I will edit here. Again, whatever group of node you had defined in mesh, those are available here. So I am going to fix the bottom. So I am selecting bottom. So it has already shown the bottom nodes. If you want to rotate it, you can in fact see it. Yes, you can see that these are the nodes that have been selected for this boundary condition. Okay, and now I have given the boundary condition. I am saying OK, and then OK. Is there anything left? Nothing. So I can say OK. Now it is OK. Then I need to apply the pressure load here. For that, again I'll go for this command, assign mechanical load. So commands BCN load, assign mechanical load. Now I will call it say load or pressure load, pressure. I am saying pressure, and then I need to select at least one from all these. I had already selected enforced DOF in another load statement. Now I should use pressure rep, press rep. This one, press rep, that means representative pressure. Okay, you know that in FEM everything should be nodal load, but here my pressure is just overall pressure. That's why it is said as representative pressure or press rep. And then I must add some item, and it is asking me which group of element you want to apply. So from this box you need at least one out of these three, and from these two you need at least one. So I will apply on group of element top. So I am selecting group of element, then I'll apply in top. So this is selected graphically, and then I should say the value of pressure, and say I give only 1 MPa load. Okay, so 1.0 megapascal, okay, or Newton per millimeter square. Since our dimensions are in millimeter and load is in Newton, so when I say it is 1, that means it is 1 Newton per millimeter square or 1 megapascal. And then I say OK and OK. So I have selected the load as BC and pressure. Now I will go for pre-analysis. In this case I do not need any pre-analysis for linear static study. That's why you should know which command is necessary in which type of study. Okay, and then I go for analysis, and here I have all these different types of analysis possible, and this is statics, so I cannot read anything here. Yes, static mechanical analysis. So I can select this, and now it is asking me the things. It is res-lin. Okay, so linear result, and then it is asking me which material field or which structural elements. So I am selecting material field material, whatever material I had assigned earlier. Okay, that material should be used. Then it asks for model, and it has already taken the model from assigning the model. Okay, FA modeling. Then it asks me what are the loads. So I have two loads now. One is boundary condition, one is pressure. So I will select two items. So first item is load, that is boundary condition. Okay. Then second load is the pressure load, right? So pressure load I am applying, and this multiplication factor or load type are necessary. Multiplication factor is necessary in nonlinear study when I apply the load stepwise. Here in this case I am applying load in a single step, so this multiplier function is not necessary. So I am telling it okay, and you should once always see if something mandatory argument is left out. Okay, I say okay. So I have created the analysis now. Then from this analysis will find only the displacements at all the nodes, okay, in all these 3 degrees of freedom. But that is not much meaningful for us, so we need to calculate something else, maybe the reaction or maybe the stresses. Okay, so for that I need to go for post-processing, and in post-processing there are many functions. We use calc shaw, that means calculate the field. Shaw means field, and I'll use I must use the same name as the analysis name. Okay, so analysis object was res-lin, so I should write the res-lin here, or I should say that reuse the object, so it will automatically use the earlier result available. Okay, and then I will calculate the contra means constraint or stress in French. Okay, and now the stresses in Code-aster or Salome-Meca can be calculated at various in various manners. One is the stresses in the element Gauss points. The other is the stresses at the element nodes, and the other one is the stresses at the nodes from all meeting elements or merging elements at that node. So depending on that, there are various terms used. I will discuss maybe in another tutorial the meanings of these terms to in a more details. Now I will just select a few of them. So I'll add maybe 3 terms. One is sigma alga. SI means sigma or stress. So you have different types of stresses: effective stress, then this is equivalent stress, etc. Okay, the meaning of all these terms I will explain later on. Now for this case I can use sigma alga. That means it is the general stress in element Gauss points. That means all those integration points I told you that in a plain quadrilateral element there will be 4 integration points. In a 8-noded brick element there will be 8 integration points. So in those integration points the stresses can be very easily calculated. In fact, yes, easily calculated, and therefore because we can easily convert the nodal displacement to those element displacements at those points by using the isoparametric transformations. Okay, and therefore I can use sigma alga, then I can use sigma L node, that means at element nodes, and I can use at actual nodes sigma NOEU. Their differences I will explain later on. And then deformation here means strains. Okay, if I select this I can also select the deformations. I will not do it, but let me just show you. If I select this I will get FC alga, FC LNO, FC NOU. FC means epsilon, and therefore I can use FC alga. Okay, but I am not doing that now for this study. In some other study it may be necessary, so I am unchecking it. And then in mechanical design it is customary to find out the von Mises stress, and for that we need to use this factor criteria, and in the criteria I will again select 3 things: sigma equivalent alga, sigma equivalent LNO, and sigma equivalent NOEU. Okay, these will calculate the von Mises stresses at the Gauss points or Tresca stresses at the Gauss points, and von Mises stresses at the element nodes or the von Mises stresses at the nodes. Okay, and then if I want to calculate, now it is asking me which result it should use to calculate these stresses. Obviously I have only one result, in this case Reslin, which was available here. So since I have said reuse the object, it has already automatically selected the result that it needs to use. That means from displacements it will calculate all these stresses. Okay, and next is I can calculate the loads. That means I can calculate the reactions. Okay, so for that let me put loads, select loads, and here no, it is not reaction, it is forces. I am sorry, I should select forces. Yes, this is my force. If I select this, then I need to add, say I want force noda. Force noda means nodal forces, and react noda means nodal reactions. Okay, nodal reactions will be calculated at the fixed or hinged or roller supports, wherever it is supported. Okay, so I am saying react noda, and then what I should say, I think that's okay, react noda. Then okay, it appears to be okay now. Calc show, these are the things will be calculated, and react noda is also calculated. So my post processing is done. Then fracture and fatigue is not there in this our model, so I am not doing anything here. And then I should give I should tell the solver to write the results in some file, and that is where this output command comes. So let me go from here, output. So it is saying set output results. Now here again I should give the result file location, just like the mesh file I had given earlier. And this is a mandatory argument, and what are the results you need, that is also mandatory, because it is accompanied by red stars. Okay, so I'll select this and I will write a name in that appropriate directory. Say I will say result box dot rmed. Rmed is the result med file. Okay, rmed, the binary format of result file is rmed, it must be provided. I'll say save, then the format is med. It will say we can use different format also. I can use tabular format, okay, I can use Aster format. I'll use both. Okay, so in the result I will write one item, and I will use not the Meca static, I want the calc show, so that everything is, the stresses also is written. Okay, so I'm applying this, and I should also write the mesh in the file. This is necessary for post processing. Okay, and this is fine. Then I can say okay, okay, fine. So now my result is there. Now what I may want is that I may want the resultant reaction, so that I can check my equilibrium. My resultant reaction should be equal to the total load applied, right? For that, what I can do in the post processing stage, I can go back and I can extract the sum of the reactions, and for that I'll have to use one command called post processing. I'll say post reliability. That means it will post process some results and create a table. Okay, now it wants the action as a mandatory element here, so I give the action as what field I want, I want from which result I need to extract the value from this Reslin result. Okay, and for which group of node I want for the bottom group of node my reactions. Okay, Then which thing I want, this is also one mandatory, one at least one of, not at least one, only one out of this is necessary. I will say resultant, because I need the resultant reaction. I know reaction because I have selected the appropriate node group. Okay, and then I can have three resultants in dx, dy, and dz. And if it is a beam or frame element, I will have also moments. That's why there is here in this case an xx is there. Yes, an xx will be useful for shell elements, and in Code-aster we have three-dimensional shell element also. That's why those forces are shown, but it is not relevant here, meaningless here. That's why I have not selected them. And then operation I need to extract the results, so I will say extraction. Okay, I'll say extraction, and I can give some title, and I will say some reaction, sum of the reaction. Okay, some reaction. Then nom-chum, name of the field. Name of the field is react node. So I should select react node. Where it is? Yes, react node. Now I think everything is given. So I need react node, and I need to extract in a table. So I'll write OK, and then OK. So this is the command, corresponding command for extracting the result in a table. Now this table must be again printed. Okay, and for that again I will go for the output command. So let me go output, and I will say imp table. That means I will print a table. Okay, so imp table, the table is automatically selected, whichever was generated in post reliability step, and I need to give the file name. I can give the file name as a reaction.out, because it will be a text file basically. Reaction.out, save, and the format is tableau. Okay, I can have different format. I can have numpy format, I can have Aster format, I can have other formats. I will say it as tableau. Okay, that means table. And I think this much is sufficient. Yes, I can tell about the format. Format are, I can say 1p e 12.5. This is exponential format in 12.5, and this 1p means it will, instead of writing say 0.1 into 10 to the power 5, it will write 1.2 into 10 to the power 4. So 1p means the decimal point will be after one digit. Okay, so it will be 1pe, or you can just write 1p 12.5. and then various separators you can tell if you want. If I don't select, it will be the default separator. Then you can give some title of the table. Title is sum of reactions I have given. Then I said OK, then OK. I think now my whole file is ready, and then I can save it once more. And now I can go to this tab, history value. history tab. Okay, now here it is automatically selected the current case, whatever case we have generated in the stage. Usually it is case 1 now, and in case 1 it is my stage 1, okay, because it was in the first stage. If you remember, all these things were in stage 1, that's why that stage is coming here. Okay, and now the case name is run case 1. You can change it, of course. Then it allows some default value of memory, 2048 MB, about 2 GB, and time is 15 minutes, it is saying. And the version of the Code-aster is 14.4. Here only you should use stable version. Number of CPU is 1, of course, because it is sequential. And before doing, you should select here auto refresh as 5 seconds, otherwise you will not know that the study has been completed. Now after all this, if I click here, this will be activated. Okay, run. So I'll click run now. Now my system will start running, and you will get this message file, and it is still running. You can see the message file. Exit code 0 has come. That means my study is okay. So green light has come. Otherwise there will be red light or yellow light if the study is not completed properly. So my study is over now. Okay, and this is the message file you get. And this message file is very important, because if there is some error, there will be some indication what kind of error it is in the alarm section. Here you can see that there is one alarm section. Here you see warnings which you choose to ignore. Number of occurrences of warning. It has said some warning has come, but no error. Otherwise there will be alarm. Okay, there will be alarm, and it will be written. If some error is there, it will be written. Now what I can do is, now you see this RMED file is generated. Okay, and this reaction.out is also generated. If I right click, it will say browse directory, or I can see this result RMED in the post-process module. So I can either go to this post-processing module and can open this in Paravis, but there is an easier way now to post-process here itself within Aster-Study itself. So I'll select, right click, and I'll say post-process. Now post-processing will be initiated. It will take little time. Because it is a virtual machine and screen recording is on, so it is, yes, now it has come. This is my box, and initially displacement is being shown. Okay, displacement is being shown, and you can see that this shadowed part was the original shape, undeformed shape, and now it has deformed. You see from here, you can see that it has become it has swelled in the other X direction or Y direction, and in the Z direction it has gone down. But here the deformation is 0. This color code is telling me that this is 0, and this is my 9.5 e to the power minus 4. That is the deformation in millimeter, because everything was in millimeter and Newton. Okay, so that means this is my magnitude of deformation. You can see dx value in the x direction. Okay, and for symmetry, whatever value is in this direction, opposite value will be in this direction. That's why this is 1.5 and this is also minus 1.5. Minus means it is opposite to the positive direction of the axis. So my x-axis in this direction, so this is negative and this is positive. Similarly, I can see dy. dy is, I should see in this direction. It is just same because it is isotropic material. And then dz, if I want to see, sorry, dz, and this will be the dz. Here the deformation is almost 0. It should be actually 0, but because of numerical rounding off, it has given me 1.1 into 10 to the power minus 19, which is as good as 0, and maximum deformation in z direction is minus 9.3 into 10 to the power minus 4. You can check these results from your analytical results. Okay, then what I can find global stress, and support reaction is also there. If I select it, my support reaction will be shown. Magnitude or dz, I can see dz, it is 2 into 10 to the power, what is the value? It is this color, 2 exponential 2. This is my support reaction. That means how much was my pressure? Pressure was 1, and I need to check whether my reaction is correct or not. And therefore, what I will do is I will open the other file where the values are written in text file. Okay, so for that, let me go to this file browser, and I had everything in box study, so I should open the reaction file. Okay, you can open it in Notepad, but it will not be good. I will tell you one more software. It is Z-Edit. Let me write it in some file, Notepad file maybe. Let me open. Yes. Let me open a text editor, this same Z-Edit. This is called Z-Edit. You should browse in Google Z-Edit for Windows. If you write that, you will get executable, and you can download and install it. This is important because the Notepad or WordPad is very bad in reading these files. Okay, so what I will do is I hope it is visible to you. Cancel Z-Edit for Windows. Okay, let me close it, and I'll open this reaction file, and you see sum of reaction react node. In dz it is 4 into 10 to the power 4, and that is perfectly okay because I had 200 into 200 millimeter, which is 4 into 10 to the power 4 into 1 Newton per millimeter square gives me 4 into 10 to the power 4, as the reaction in z direction, and in dx and dy direction they are very very small, 10 to the power minus 11 and 10 to the power minus 13. Those are actually for numerical rounding of those values are coming. Ideally it should have been 0. Okay, and it has taken place in instant 0. Okay, that means in the first load step, because I have only one loading step, my result is this. So this is why to check your result, writing some of the important things in a text file is very important. Okay, and that's why I had generated that table and wrote it here as reaction.out file. Okay, now going back to our post processing, so these are support reactions. I can say equivalent stress at integration points, CF elga, or basically I should get sigma elga. This is my global stress. This is C sigma in XX direction. Then I can see sigma in ZZ direction, and you can see that this is 1. You see this color is 1 because I have applied 1 megapascal here, 1 Newton per millimeter square, and at the bottom also it is same, nearly same. At the corners it is very very small, not small, it is more because of stress concentration. That's why at the corners you get 1.8 into 10 to the power 0, 1.8, that means, and it is negative because it is compressional. Okay, it is negative because it is compressional stress. If you want to see the sigma xx, you can see this is normal stress in x direction, this is normal stress in y direction, and this is sigma xy. That means sigma xy means this shear stress on x plane, on this plane in y direction. Okay, this shear stress. So in this direction, this is sigma xy. In this direction it will be sigma xz. So I can see that also, sigma xz. These are the values. 0. There is no shear stress. Okay, and if you want to see the stress condition inside the thing, then what you can do is you can change the transparency. I think here it is opacity is 100%. If I use say 50% opacity, then you will see apply. It'll take some time. Now you see I can see the inside also. All the elements I can see, and their stress condition is nearly same. Okay, so like this you can post process the results. So with this we complete this study. Let me save the study here, and let us stop the tutorial now. Thank you for watching. I hope it was useful.